Hello, it's Keith here, and this is the first in the 65816 series of my assembly programming tutorials. The 65816 is the 16-bit equivalent of the 6502, it was the upgraded version, and is most famously known as being the processor of the Super Nintendo. In this series we're going to be looking at how the 6502 was extended and upgraded into the 65816. We'll be discussing the new commands, the new addressing modes, how the commands have changed with the new functionality, and we'll be learning all about that, but we won't be covering the existing 6502 functionality. Now, any command that we discuss I will explain in entirety, but I'm assuming you will know or learn how to do the basic 6502 stuff, because you will need to know all of the 6502 functionality for the 65816, because the 65816 actually starts in 6502 mode. So what I would suggest is, if you don't know the 6502 yet, take a look at my 6502 assembly programming tutorials on my YouTube channel, because it's possible you don't even need to know 65816. You can do basic Super Nintendo programming in just 6502 mode. Alternatively, if you're interested, I do now have a book for sale on Amazon. It's called Learn Multi-Platform Assembly with Chibi Akamas, and it covers Z80, 6502, 68000, 8086 and ARM, and if this book is a success I will do one on the 65816 as well in the future, so please consider buying my book and supporting my programming tutorials. Anyway, we're going to be going into today the new functionality of the processor, the extra registers, how they've changed, and how we switch between the standard 8-bit 6502 emulation mode and the new 65816 functionality, which increases the size of the registers and things like that. So we're going to learn all about that. Now, first of all, we're going to discuss the registers and the flags. So the classic 6502, of course, had an 8-bit accumulator. The new 65816 has two 8-bit accumulators which combine together to be a single 16-bit accumulator. So in 8-bit functionality, these are known as A and B, and we can switch those two around at will. In 16-bit mode, they become a single accumulator which is known as C. It's not D like the 6809, it's C in this case. So that is a 16-bit accumulator. The X and Y registers have also been extended to 16 bits, although there is no split. They're just either in 8-bit mode or 16-bit mode. And as we'll see later, when we switch to 8-bit mode, the top byte of the 16-bit version is lost. The stack is now 16-bit, the program counter is still 16-bit, and the 0 page is now relocatable, although only within the first segment, so it can go from 0 to 65535, but it can't go into a larger addressing space than that. Now, our addresses, like the program counter, is still 16-bit, but we now have some extra registers that are 8-bit that make up the extra 8 bits of the full 24-bit addresses. So when we use X and Y as indexes, the top 8 bits will be made up of the data bank register, which is sometimes referred to as B, and the program counter will be made up of the program bank register, which is sometimes known as K, and we'll see that in some of the commands later on. So this is how we've extended the processor so that it can support 24-bit addressing from its original 16-bit addressing roots. Now, the processor itself starts in classic 6502 mode, and to turn it into full mode we need to disable the emulation bit. Now, the emulation bit is a special flag, but it doesn't appear as part of the standard processor flags. What we actually do is we set the carry accordingly, and there's a special command to switch that status into the emulation flag, and that will turn on or turn off the 65816 functionality. As I say, the processor starts in 6502 mode. Now, in 65816 mode we have two new processor flags. These are the memory and accumulator select, and this will turn the memory, that's the commands that work on memory addresses, and the accumulator commands into either 8 or 16-bit. If we set that to 1, it's 8-bit. If we set it to 0, then they're 16-bit. And there's a flag to set the X and Y registers to either 8 or 16-bit in the same way. And we can have, and we'll see this later on, we can have the accumulator as 8-bit, but the X and Y registers as 16, vice versa. We can have both as 16-bit or both as 8-bit, and we can have both as 8-bit in 65816 mode. So it's very unlikely you're going to want to switch your processor back to 6502 mode once you're into 65816 mode. Another curious thing about this processor is we've gained lots of commands, the most simple of which would be XBA, which swaps the A and B registers over. Now, these actually work in 6502 emulation mode, which sounds ridiculous, but that is the case. Now, essentially, if you're a very advanced 6502 programmer, you might have used what's known as the undocumented opcodes in the past. These now no longer function the same as they used to. They are now the opcodes of the new commands. And if you use those in 6502 mode, in a lot of cases, you will get the functionality that they provide in the 65816, so you won't be able to use those undocumented opcodes anymore, although I suspect if you were using them, you're probably way more advanced than anything I can teach you, so you're probably not watching this video. But anyway, it's another thing that's quite curious, and again, we're going to see that today. Now, let's go over to our source code view and let's see some action. Okay, so our tutorials today and the tutorial set that you can download from my website, you can download my build scripts and the development tools that I use, and also the examples. The only thing is I can't give you the ROMs for the Apple II GS. You're going to have to find your own, so that might be a little bit tricky for you. But a lot of the tutorials we'll be viewing today will be working on the Super Nintendo and also the Phoenix. The Phoenix C256 is a new development platform that's being designed, and that is also 65816 based, so we can use that as well, although the fonts are a little bit smaller, and we will be focusing more on the Super Nintendo because I think that's what you're going to want to use. You know, that's the most common platform out there. Now, you can go to my website and you can get this minimal multi-platform example which shows a hello world message on all of these systems. Here it is running on the Super Nintendo, and you've got a basic register dump of the new 16-bit registers and also some memory there. That's the Super Nintendo version. We also have the Apple II version here. If we just skip through here, there we go. So here is a dump on the Apple II, and it also works on the Phoenix as you just saw. So there it is. It's rather small, but that is indeed the Hello World example running on the Phoenix 256. So, I mean, as always, I've tried to give you some standard scripts to get you started and hopefully allow you to do a bit of testing and debugging as quickly as possible so that you can get into the real interesting stuff of playing around with this processor rather than working out how to get things running. So, this is lesson 1. This is what we're going to be looking at today. So first of all, we are starting the process and we're setting it into 16-bit mode. Now, we need to use 16-bit mode for the Phoenix 256 because that machine needs to be, it needs 16-bit to access the VRAM, but we can also turn back to 6502. So what we're doing here is we are starting in, we're clearing the carry, transferring the carry to the emulation bit, so that sets the emulation bit to 0, which turns on 16-bit mode, which is known as native mode, and then we are just starting our screen initialization and clearing the screen, and then we're jumping to the first example, which is the mode switching example. And what we're going to do is we're going to switch between 8 and 16-bit mode, and we're going to set some registers and see how the functionality changes and the values in those registers changes. So the start of this example, we're going to set the carry and transfer the carry to the emulation bit, and that switches us back to 8-bit mode. Now, because the commands use the same bytecode once they're compiled in 8 and 16-bit mode, we actually need to tell the assembler what the state of the processor is in. And here we're telling the assembler to create 8-bit code. So we're telling our assembler that the accumulator is 8-bit and the index registers X and Y are also 8-bit. Now, I'm using the assembler WLA. If you're doing things with a different assembler, these will be different. It depends entirely on your assembler. These aren't commands, these are assembler directives, so you would have to check your own assembler. Now let's fire this up on the Super Nintendo and let's see what has happened. So we first set our processor into 8-bit mode by setting the carry and transferring that with XCE from the carry to the emulator bit. X is of course short for exchange. We've then told our assembler that our accumulator and our index registers are both 8-bit, which they will be by default in this mode. We're then loading an 8-bit value into the accumulator and an 8-bit value into the X register, that's the value 66 there, and the value hexadecimal 66. And then we're loading from memory address 66 into the Y register, and we're showing the monitor. And you can see that over here. So the C register, which is the B and A registers there, the A part has been set to 66. The X register has been loaded to the value 42, which is 66 in hexadecimal. And the Y register has been loaded in for a 0, which will be what is at memory address 66. So that's what has happened there because of our commands. Now, if you don't know any assembly for 6502, the dollar symbol defines hexadecimal. So hash $66 says the value hexadecimal 66. Hash 66 means the decimal value 66. And Y with just 66 on its own means the memory address 66. The lack of the hash symbol there means it's an address. So there we go. Now we're in 8-bit 6502 mode. Now XBA, which is exchange B and A, is swapping the B and A registers, and even though we're in 6502 emulation mode, this does still work, as does TXY, which is transfer X to Y, which is another 65816 command, but these both work in 6502 mode. So you can see here that our two parts of the C register, the B and A accumulators, have swapped over there. And in this one, our X register used to be 42 and our Y register used to be 0, but the 42 has now transferred from the X register to the Y register thanks to that TXY command there. Now that's how the processor will work in 6502 mode, but of course we want to have a go with the 65816 mode. So what we do is we clear the carry, set the carry to 0, and then we exchange the carry and the emulation bit here. Now that will switch us into 65816 native mode, but we still need to tell the processor to turn the accumulator and the memory and also the X and Y registers to 16-bit. So we're going to use the command rep, which is a reset processor flags command, and this will reset where we specify a 1-bit, the bit in the processor flags to 0. So we are specifying these two bits here should be cleared to 0. And these are the M flag and the X flag. And the M flag is the accumulator and memory status, and the X flag is the X and Y register status. And resetting these to 0 sets them to 16 bits. Now, because we've set those to 16 bits, we now need to tell our assembler with the assembler directive that it needs to start producing 16-bit commands for those, because the bytecode will be different. And so now what we're going to do is we're going to load our accumulator with the 16-bit value 6660. We're going to load the X register with the 16-bit value 666 in decimal, and we're going to load the Y register from the memory address 666. Now that's of course a 16-bit address, which we could have done before, but before we would have only loaded a single byte, and now we're going to load in 2 bytes. Now if we go over here, we can see our C register, which is the 16-bit accumulator, has been loaded with 6660 as we requested. The X register has been loaded with hexadecimal 29A, which I guess is 666 in hexadecimal, I assume it will be. And then you can see our Y register has been loaded with a 16-bit value there. That will be at memory address 666. Okay. Now that's how the processor functions when we reset the 2 bits M and X in the processor flags to 0. If we use the SEP command to set the processor flags to 1, the 2 bits marked as 1 here will be set to 1, the others will be unchanged. We've now set the 8-bit mode for those X and Y registers and the accumulator and memory functionality. We now need to tell our assembler that we've done that. So those are setting to 8-bit again. And this will actually immediately affect our X and Y registers. So if you remember before, our C register was 6660 and it is still 6660, but our X register was previously 029A and now it is 009A. Our Y register used to be A84A, it's now 004A. The top byte has been zeroed. Now, it's not just a temporary thing. It's not just that when we change that functionality, they go to 0, and when we reset it, they come back. If we do another reset and switch those back to 16 bits and tell the assembler we've done that, well, those values do not come back. Our C register has never changed, so there's nothing happened there. But our X register, the top byte, now we're back in 16-bit mode for the X and Y registers. Well, those haven't come back. It's not just that they were being ignored, they've actually been zeroed, so the value has gone, which may be a problem for us, it may not. Now, in those examples, we were switching both the accumulator and memory, which are a single unit, and the X and Y registers to 8 and 16-bit together. We can do them separately if we require. We may want to work on 8-bit values in our accumulator and memory, but use 16-bit X and Y registers, or vice versa. We can do that. In this case, we're using the SEP command to set the M flag, which is setting the accumulator and the memory to 8-bit, but we're resetting the X flag, which is setting the X and Y registers to 16-bit. So now we have a combined combination, and now we need to tell the assembler with those directives that the accumulator is 8-bit, but index registers X and Y are 16-bit. And now we can do this. So we're loading the A register with an 8-bit value and the 16-bit register with a 16-bit value. Now, and of course, if our assembler thought the X registers were still in 8-bit mode, we would not be able to load that 16-bit value in. And if we loaded an 8-bit value in 16-bit mode into our accumulator, the assembler would figure it out. It would add some zeros, but we'd effectively make a 3-byte command where maybe we only need a 2-byte one. So again, it just depends. So there we go. So we're loading the hexadecimal value 88 into our accumulator there. And you can see that has happened here, but because we loaded it as an 8-bit command, the top register part of the register, the B part of the B accumulator, so to speak, of the C double accumulator is still 66. It's been unchanged by that 8-bit command. The X register, though, because it's in 16-bit mode, has correctly loaded with that 16-bit value there. So that's what happens if our accumulator is 8-bit and our index registers are 16-bit. We can, however, do the opposite. Here we're resetting the accumulator and memory, so they are now 16-bit, and setting the X flag to 1, which is setting the X and Y registers to 8-bit. We're then telling our assembler with those assembler directives that's what we've done. And now we're loading a 16-bit value into the A accumulator. That will be the C accumulator there because it's 16-bit. And we're loading an 8-bit value, 99, into the Y register here. And you can see that that has happened just here. So now we've loaded that 16-bit value into the C double accumulator there, the 16-bit accumulator. Our X value has changed back to an 8-bit value, so the top byte has been lost again. And the Y register has loaded with that 8-bit 99 value there. So that's how we can work with 8 and 16-bit registers. We can switch between them. We can have our X and Y as 8 or 16-bit and our accumulator and our memory functions as 8 or 16-bit, and we can swap between them, and we just need to tell the processor by setting and clearing those flags, and also tell the assembler what kind of commands to compile, because unlike a system like the 65816, we don't specify that the commands are 8 or 16-bit in line. There's no .l.s or anything like that. We have to use the assembler directives to do that. Now, during that, I was referring to the accumulator and the memory being switched to 8 and 16-bit by the M flag, and I know I didn't explain what I meant by the memory. We will see that now, though. Basically, all of our commands that before worked on 0-page entries or direct memory, absolute memory addresses, they will now work at 16-bit as well when that M flag and the accumulator are set to 16-bit. And we will see that with this example here. Okay, so what are we going to do? Well, first of all, what we're doing here is we are using the reset command here to set the M flag to 0, and that is setting the accumulator and the memory as 16-bit. And then, of course, we need to use the assembler directive to tell it that the accumulator and the memory are now 16-bit, and that will compile the commands correctly. So what we're going to do is we're going to loop 10 times. We're going to load the accumulator with a 16-bit value there, and we're going to store it to 0-page entry HL. Now these are just 2 bytes in the 0 page that I've defined, and we're then going to load the accumulator with a second value here. And then what we're going to do is we're going to arithmetic shift left the accumulator, and we're going to increase the 0-page entry HL. So that's just 2 bytes of the 0 page there, and we're going to see what happens as we repeat that 10 times. So, well, what happens? Well, our 16-bit accumulator, the C accumulator, is 4321, and you can see as we run iterations, those bytes are moving across. So, for example, here at the start we had 4321, but after we've done 4 shifts, the bottom nibble has become 0, and the other 12 bits have moved across because we're now working in 16 bits, so that's become 321. On HL, which was our 0-page entry, our inc commands are now working at 16 bits, and this is what it means by memory. Our inc command isn't working on the accumulator, it's working on the memory, but those memory commands are all now 16-bit. So you can see here that as we did A2FC, A2FD, A2FE, A2FF, well, after our 0-page entry HL went up over FF, it became 81 here. So you can see those commands are all working in 16-bit on memory, and it's not just the inc command, it's all the commands. So if I change this to an ASL here, so instead of inking HL, I'm now doing an ASL of HL, and if I run again, where you can see our 4321 is shifting across, and that becomes a 321 there. Well, our HL is now also shifting to the left in 16 bits. So if we go down here, we see that our A2FC becomes a 0FC0. So our commands, all of our commands that used to work on memory, like inc and ASL, can now be switched from 8 bits to 16 bits, and they'll work on those 0-page or direct memory addresses in 16 bits now. Now that was the 16-bit test. This time we're going to do an 8-bit test. So we're loading the same values into the accumulator and the 0-page. We're then setting the M flag to 1, which means the accumulator and the memory will now be 8 bits. And we're doing those same commands again, the arithmetic shift left and the inc of the 0-page HL. And this time we will see a difference. So this time we're only shifting an 8-bit value. So you can see that the 4-3 top value, which is in the C register, which is of course 16 bits, and that's the top byte is known as the B accumulator, and the bottom byte is the A accumulator. So you can see that the B accumulator was never changed because that's now an 8-bit accumulator, thanks to that memory flag, the M flag, being set to 1. And when we did our inc of the 0-page entry HL, now that was only affecting a single byte. So when that single byte went to FF and rolled over, the top byte, the next byte along in the 0-page, was unchanged because it's now only an 8-bit command. Whereas before it was changed along with it because the memory commands were working in 16 bits. Now, I know all of this is a bit confusing. I mean, it probably will seem as such. So what I'd suggest you do is you go to my website, you download the build scripts and the example files, and you have a go with all of this yourself, because we're going to be going over this more in the future. But you know, there's really nothing better than trying this all out for yourself, seeing it in action, changing the values yourself, and seeing how the values in memory and in the registers change accordingly. And that's why I give you the scripts that will allow you to do that, you know, the test script. My Hello World example has a mem dump for dumping areas of memory and a monitor for showing the values of the registers, so it should help you get started. I also have a new cheat sheet which includes all the 6502, 65806, and also some other weird processors like the 6280, the PC Engine processor. All of those are included, and it's been extended to support the new addressing modes. So please download my 65816 cheat sheet, which should help you get started with this processor. Now, this was the first lesson, and I'm sure it was a little bit daunting because we've gone over it a little bit quickly. But if you like what you've seen, please like and subscribe, because there will be more videos coming. And if you like the videos, YouTube recommends them to more people. The other thing is, we've only covered the very bare basics of the processor, discussing switching the modes and also how that affects the registers. Next time we're going to go into more detail on the addressing modes, and we'll learn more about the new addressing modes and how the 24-bit addressing really works, which is a big thing, especially if you're using the Phoenix C256, because you can't get to the VRAM on that system without working in the 24-bit addressing mode, whereas on the Super Nintendo, as I say, you can technically get away with writing a simple game in just 6502 mode. Once again though, I'd remind you, if you need to know about 6502, if you've just jumped into this not knowing any 6502, please take a look at my other assembly programming tutorial series. If you just search Chibi Akuma's 6502, I'm sure it will come up. And also, if you would like to support this channel and you want something in print, please go onto Amazon, and if you have a look, if you search for Chibi Akuma's, you will find my book, and there'll be a link below in the comments. You can buy my book, which covers 6502 assembly programming, and I hope that will help you out as well. I'm pretty sure it will. Anyway, I hope you found this interesting. I hope you've enjoyed it. Thanks for watching today, and goodbye.